If you are a slide counter, what I'd like to do is get through part 2 entirely into the first assignment slide in part 3. So we shall see. We just kind of need to stay on track. So we talked about strong acids, strong bases, weak bases. The strong acids and strong bases are a one-way arrow. Weak acids, weak bases are a two-way arrow. And they're described with what I call a Ka expression, equilibrium, and a Kb expression. So with that in mind, we need to focus on what is pH. Well, of course, P is a lowercase p and uppercase h. But the P is more broadly than pH. P function is basically negative log of whatever. So I brought my calculator here to kind of be playing around with here in a minute. So pH means that it is actually the negative log of the molar concentration of the hydrogen ion. Okay? We're going to be broadening that out and looking at pOH, which is negative log of the molar concentration of the hydroxide ion. Another P function we're going to apply is, remember those Ka's, the ionization constant of a weak acid? The pKa would be negative log of the Ka value. Okay? Literally. So we'll kind of do some examples of those. So in just plain old water you expect to be neutral, and we're going to talk about more what neutral means. If you think you know what it is, you do. Okay? Neutral basically means that you have the same molar concentration of the hydrogen ion and the hydroxide ion. Just plain old water left to its own accord, okay, is going to auto-ionize. To a certain extent, it's going to fall apart and give you the hydrogen ion and the hydroxide ion. Okay? Of course, what we've got there, we've got an equilibrium, and we've been talking a lot about equilibria in Unit 3 and now in Unit 4. It's the molar concentration of the products divided by the molar concentration of reactants, all raised to stoichiometric coefficients. If it is an L, okay, it does not show up in your Kc or Ksp or Kp or Ka expression. I got a lot of Ks, okay? So Kw is talking about the auto-ionization of water, and it's just the molar concentration of the hydrogen ion times the molar concentration of the hydroxide ion. There is a value for Kw, and there's an arrow there, so you're going to want to commit it to memory. Kw, the value for Kw is with 4 sig figs, it's 1.008 times 10 to the negative 14th. I'll go ahead and write underneath it. With 3 sig figs, it's 1.01 times 10 to the minus 14th. Okay? So remember the units for our equilibrium constants, whether they're Kc's, Kp's, Ksp's, they're unitless. So it's unitless. But that's the molar concentration of the hydrogen ion times the molar concentration of the hydroxide ion at 25 degrees Celsius. So with the auto-ionization of water, if we look at the stoichiometry, you know, you just got ones across the board. It's the most boring stoichiometry. You have 1 mole of this, we'll give you 1 mole of this, and 1 mole of this. So in other words, these are equal, okay? So if this value is the product of these two things, okay, if you take be the square root of this, okay, you get 1.14.5. Yeah, it's like, really? Yes. Take the square root and you get however many sig figs you're going to go with. I probably am questioning this. If you know this to 4 sig figs, I don't know why this is only 2 sig figs. But anyway, it's a magnitude of 10 to the negative 7th. So in just regular old water at 25 degrees Celsius, the molar concentration of the hydroxide and the hydrogen ion is 1.0 times 10 to the negative 7th moles per liter. So I have a couple of videos to show you. Now notice how this is auto-ionization too. It's a little bit different. We kind of have what I call a carrier water molecule to kind of pick up the hydrogen ion, make it the hydronium cation, okay? But it's really the same thing. And we kind of talked about that on Friday. Let's see. All right. So, showing you the auto-ionization of water again. Kind of the second version. If we take just a minute and talk about the Bronsted-Lowry definition of an acid as a proton donor, here on the left side, on the reactant side, let's see, which one's a proton donor? Doesn't this make sense that this is being the proton donor? Because over here it's minus the proton, and this is being the proton acceptor. Okay, so that's the sort of thing we talked about the other day. Okay. So KW is talking about the auto-ionization of water, but as it turns out, in any relatively dilute aqueous solution, even if it's not neutral, the hydrogen ion concentration is not equal to the hydroxide ion concentration, the product of the two is KW, which, committed to memory, 1.008 times 10 to the minus 14. Okay. Let's take a little closer look at the whole pH and pOH, okay? So pH is, we're applying the P function, which is negative log, in this case, of the hydrogen ion, the hydrogen ion concentration. pOH, negative log of the hydroxide ion concentration. Now, this might seem like a little bit of magic. By the way, in my notes, anytime you see a box around something, that's like a tool almost that you might use for your problems. You probably kind of picked up on that. If we take 10 raised to the pH is equal to 10, before I do this, I probably would multiply through by minus 1. Say multiply through by both sides by minus 1, and I got negative pH is equal to positive log base 10 of the hydrogen ion concentration. Now, if we can do the same thing to both sides. If I take 10 raised to the negative pH is equal to 10 raised to the log base 10 of the hydrogen ion concentration, this right here simplifies to the hydrogen ion. Okay, so that's why this relationship is true. 10 raised to the negative pH is equal to the hydrogen ion concentration. Similarly, 10 raised to the negative pOH is equal to the molar concentration of the hydroxide ion. These are very helpful in problems, in your homework, in tests, in your lab. Okay, they mean the same thing. Okay, so we said KW is equal to, for dilute aqueous solutions, the hydrogen ion concentration times the hydroxide ion concentration. Here's one for you. This is the law of logs. If we take negative log of this quantity is equal to negative log of this quantity, okay, I don't know if you remember, but of course this would go to be pKW, and this thing, if you have the product of two things, it's actually, it's the sum of the individual logs. So this thing comes out over here. It's the pH plus the pOH. So bottom line is we have kind of another thing that might be helpful. For a same solution, okay, did I tell you what pKW is? Not yet. But if in your calculator, I'll just go ahead and let the cat out of the bag. If KW is 1.008 times 10 to the minus 14th, if you plug that into your calculator, you are going to get 14.00. So for the same solution, pH plus the pOH is equal to 14.00. Okay. So these are all tools, and it's almost easier to show you and for you to wrestle with those tools in your homework and hopefully in your lab write-ups. So if you do them many times, hopefully it will sink in and you can do it on the test, quite frankly. Okay. All right. So I feel like kind of redundant with some of these slides. I'm like, we already said that. Okay, so we're going to work some problems. For a given solution, you should be able to knock out 4 values. For a given solution, you should be able to come up with, for that solution, the hydroxide ion concentration, the hydrogen ion concentration, the pOH, and the pH for one solution. And actually, we're going to kind of play around with that. So if you've ever heard kind of pH runs from 0 to 14, that's ballparkish correct. It can actually be less than 0, and it can be greater than 14. Of course, halfway between 0 and 14 is 7, and 7 is neutral pH, where your hydrogen ion, your H plus, is equal to the molar concentration of your hydroxide ion. That is true. Okay, so that's the tipping point. So I have another video, second of 2. A practical sort of eyeballing what pH is to kind of get a fix on it. Again, this is one of the things, one of the battles I fight. You already have a sense of what pH is, but we're going to be talking about it in terms of chemical equilibria. So you already probably knew that a high pH means it's basic, right? A high pH means, or excuse me, a low pH means it's acidic, and you're totally right. pH of 7 means it's neutral. But at any given point, if you were to look at the hydrogen ion, the H plus, for a pH of 1 is 10 to the minus first. For that same solution, the hydroxide ion, the OH minus, is 10 to the minus 13th. You multiply these together and you get 10 to the minus 14th. That's my point. We could step up to something that's less acidic. The hydrogen ion concentration is 0.001 molar, 10 to the negative third. Of course, that means your hydroxide ion needs to increase. As this decreases, this must increase because the product remains the same. Okay, 1 times 10 to the minus 14th, okay, et cetera, et cetera. Okay, neutral, okay, the hydrogen ion, the H plus, and the OH minus, the same. Going on the basic side of neutral, now we have a pH of 9. If I were to take negative log of 10 to the minus 9th, I would get 9. If I were to take negative log of 10 to the minus 5th, I get 5. You're kind of seeing a pattern here. Basically, ballpark, skipping whatever the coefficient of that value is, the power of 10 is the P function value, okay? So that's basic, okay, basic, and basic. All right. So these are just kind of some everyday things. I was looking at this afternoon, getting ready for lecture, and it seems like there's a lot more things that are acidic than there are basic, but some kind of everyday things that you might interact with. So I told you to commit to memory, and I think 3 sig figs would probably do you instead of 4. But I said at 25 degrees Celsius to memorize KW. 1.01 times 10 to the minus 14th. But it has a different value at different temperatures. And I never tracked this down, but this makes sense. So you figure as you get warmer, okay, the KW gets greater. And we talked about in terms of the temperature effect on KCs. If you change your temperature, your KC is going to change. Well, we talked about that. And actually, this is a case where as you increase temperature, it's going to favor the product side, because what is the product side? Okay, that is the ionized version of water, an autoionization. So this actually is a situation where that means that your heat must be on your reactant side, so it's an endothermic reaction. So autoionization is an endothermic reaction. So this is just consistent with Unit 4. And so I tracked it down today on the internet, because the internet never lies. And it was like, yep, The autoionization of water is endothermic because at increased temperatures, the Kw value increases. I'm like, yes, that's totally what we talked about. So, okay, so let's work a couple of problems, kind of find our way through those 4 quantities, okay, for the same solution. We're going to go strong and not weak. Strong because it's a one-way arrow. It's easier to get a fix on the molar concentration of the stuff. Okay, so hydrochloric acid was one of those strong acids, 6, 7 strong acids you need to memorize. Barium hydroxide is a strong base, okay? Okay, and so let's come up with those 4 quantities. So the strong acid. So if this is the case with HCl, what I've kind of gotten in the habit of is writing 0.10 molar here. It breaks apart entirely as indicated by the one-way arrow, and you have 1.01 molar the hydrogen cation and 0.10 molar of the chloride ion. But of course what we're interested in is what is the H plus doing. So the molar concentration of your H plus is 0.10 moles per liter. That is actually one of the 4 quantities we're after. Now there's different ways to get to the other 3. I'm going to show you this one. If we put that in our calculator, if you take log of 0.1, log log of 0.1, okay, you get -1. And you're supposed to take that times -1, so that's 1. Okay, so the pH actually is 1. Now, remember when I said when you apply the log function, or when you take the log of something that has 2 significant figures, I said you show the significant figures in the decimal. Okay, so I want you to, as much as possible, get into that habit. And there's a few places in my slides where I'm not consistent with this, but we have 2 significant figures in the molarity. To show 2 significant figures, it's 2 digits past the decimal. All right, so there's 2 quantities. Now this really diverges here, so what are we going to get next? Well, actually I'm going to show you 2 different approaches. Okay, so this is one approach. Can't remember what I do next. Oh yeah. So I can knock out the pOH by simply recognizing for the same solution the pH plus the pOH is 14.00. I can rearrange that, and of course the pOH is 14.00 minus the pH. Plugging in the pH of 1.00, the pOH is equal to 14.00 minus 1.00. And yes, you probably do need to show this on your homework and or your exam to get full credit, even though I can probably do that math. You show me where you came up with 13.00 if you want full credit. Okay, that's pOH, bottom line. So that's the 3rd quantity of 4. So, can't remember how I did the last one. We could do it a couple of different ways, even here. Okay. So I'm going to take the pOH, and I'm going to find I have a 10 to the x power. So if I push, see, it's been so long since I did this. If I push 10 to the x, and I put in -13, okay, that gives me 1 times 10 to the minus 13th. And that is the molar concentration of the hydroxide ion. Now, again, we're kind of, if we're going backward, kind of from a log to a normal number, we have 2 significant figures balled up here. We show the 2 significant figures in the molarity in the coefficient. So that's why it's 1.0 times 10 to the minus 13th moles per liter. So that is actually the 4th of 4 quantities for this strong acid solution. And it never hurts to say, well, does this make sense? Yeah, it makes sense that the molar concentration of the hydroxide ion is way down there. Okay, and we could do some checks. We could take this times the hydroxide ion, hydrogen ion concentration, excuse me, and we could get 1 times 10 to the minus 14th. It should all work out. The alternative approach looks like this. once we had the hydrogen ion concentration, we could recognize that the molar concentration of the hydrogen ion and the hydroxide ion multiplied together is Kw at 25 degrees Celsius is 1.01 or 1.0 times 10 to the minus 14th. Rearrange that for the hydroxide ion. So hydroxide ion concentration is Kw, which is 1.0 times 10 to the minus 14th, divided by the hydrogen ion concentration. And remember, the hydrogen ion concentration we knocked out really quickly because it was a strong acid, and we said that was 0.10. So now when you divide Kw by the hydrogen ion concentration, you do get 1.0 times 10 to the minus 13th. It's the same thing. So then to finish that thought, to get the fourth quantity, we need to apply the P function to get the pOH. We would take the log of 1.0 times 10 to the minus 13th times minus 1. That's how I think of it, negative log of the hydroxide ion. So if you were to do that, I wonder if you could just put negative log of 1e negative 13. Oh, see? If you do that, you come up with a value of 13, which again is fine. But remember, we're trying to show two significant figures, okay, as balled up in the molarity. Okay, this is the molarity with two significant figures. So even though your calculator says 13, to show two significant figures, you have to show them as trailing zeros after the decimal. Now, if there are numbers after the decimal, those are the ones that you round. They won't always be that nice and tidy like that. Okay, so let's do another one. Let's do the barium hydroxide. So for the barium hydroxide, one of the things you need to recognize is, well, a few things. It's a strong base, and it ionizes completely. Counting on you to know that. And if we say that this is 0.0025 molar, I'm counting on you recognizing that the molar concentration of hydroxide ion would be twice that, 0.0050 moles per liter. Okay, why? Because you've got two. Okay. So now, actually, that's the answer to one of our four quantities. Okay. So the molar concentration of the hydroxide ion is 0.0050 moles per liter. And then we kind of massage out probably the pOH next, right? Or you could go the hydrogen ion if you wanted to. But the pOH then is we take negative log, and actually, you don't even have to take it times negative 1. You just take negative log of 0.0050. Two sig figs balled up there. So you need to show two sig figs then after the decimal on your number. Ooh, finally got something that's not 0.00. So when you put that in your calculator, rounded to two significant figures, it's 2.30. That's the second of four quantities. Now we kind of diverge and have a couple of different approaches here. I'm going to show you this one first, where you knock out pOH once you have the pH. So, sorry, I'm going to knock out, pH once you have the pOH. Added together, they're 14, so kind of rearranged then. The pH is 14.00 minus the pOH. So in this case, it's 14.00 minus 2.30. Okay, giving ourselves two decimals, you should come up with 11.70 as the pH. Seems reasonable. It's a basic solution. I buy that. So then the last quantity we need is the hydrogen ion concentration. And once we have the pH, we can take 10 raised to the negative pH to get the hydrogen ion concentration. So 10 raised to negative 11.70. I just think that's so cool. 10 raised to negative 11.7. I got 1.995 times 10 to the negative 12. Okay, so we're going to round to 2 significant figures because that's kind of what we carried with the P function from pH. And we're going to represent 2 sig figs in our molarity in the coefficient. So yeah, 1.995 blah blah blah. Round to 2 significant figures is 2.0 times 10 to the minus 12. That's why not. Alternate approach was once you have the, what is the alternate approach? Once you have the hydroxide ion, which we knocked out from the salt as it broke apart, and remember we got 2 moles of hydroxide for every 1 mole of hydrogen ion, we can rearrange that and get the, I should say 1 mole of salt. We could rearrange that to get the hydrogen ion. Hydrogen ion is equal to the Kw divided by the hydroxide ion concentration, which we said was that 0.0050. So the hydrogen ion rounded to 2 significant figures should give us what we came up with before. And sometimes doing an alternate approach, you get a slightly different number. But the molar concentration of the hydrogen ion is that 2.0 times 10 to the minus 12 moles per liter. And last but not least, in this approach, we need to knock out the pH, and so we take negative log of that, the hydrogen ion concentration. So negative log of 2.0 times 10 to the minus 12th and see, you already kind of know what it's going to be by looking a little bit at the magnitude of the exponent of 10. Okay. But your calculator will say it is rounded to 2 significant figures. 2 significant figures because we have 2 significant figures in this molarity. To show 2 significant figures, we need to have a trailing 0. And that's it. So we must be bumped up against almost an assignment slide. So in general, the term acidic simply means that your hydrogen ion concentration is greater than your hydroxide ion concentration. Okay? And in context of what we've just been talking about, that means the molar concentration of your H+, your hydrogen ion, is greater than 10 to the negative 7th, and your hydroxide ion is less than 10 to the negative 7th. For an acidic solution, your pH will be less than 7, and your pOH will be greater than 7. I have a similar slide for basic solutions. So your hydroxide ion is greater than your hydrogen ion. For basic solutions then, the molar concentration of your hydrogen ion is less than 10 to the negative 7th moles per liter. The molar concentration of a hydroxide ion is greater than 10 to the negative 7th moles per liter. Your pH, we all grew up knowing this, basic solution, your pH is going to be greater than 7, but now we know that your pOH is going to be less than 7. So we're kind of combining what we grew up with or knew in context of something maybe a little bit different. Neutral solutions, the molar concentration of both your hydrogen ion and your hydroxide ion is equal. So that means that they are both, if your Kw is 1.0 times 10 to the minus 14th, square root of that gives you the molar concentration of your hydrogen ion, your hydroxide ion. Of course, neutral solutions will have a pH of 7, which we grew up knowing. The pOH will also be 7. So this is kind of I don't know if there's a blue box coming up around this, but when we get going working problems, sometimes you'll need the Ka, and you will not have the Ka, but you will be given the pKa. In context of what we've just been talking about, kind of undoing a P function, you need to be able to get to the Ka by taking 10 to the negative pKa. So stick that one away. So we'll take a look at these assignments right quick. 16. Okay, there. So this one is kind of like, you know, we did 2 solutions. This one has 1, 2, 3, 4 solutions. They are all either strong acids or strong bases. And you don't need 4 quantities. You just need to knock out the molar concentration of the hydronium ion. Same thing as molar concentration of the hydrogen ion, and the hydroxide ion concentration. So I don't think I have a lot of hints for that one. You guys should do fine. Just like we did. And my thing with the strontium hydroxide is don't forget you're getting 2 moles of hydroxide for every 1 mole of the salt. So don't let that throw you off. This one then is going after just one of the 4 quantities, just the pH of the solution. And it looks like I kind of picked on D, which is the strong base barium hydroxide. So you should do fine there. Okay? All right, so let's take a look at maybe the first problem in part 3. Okie dokie.